Hello, my name is Cameron Lack. I will be presenting my autonomous vehicle design in Arduino and LabVIEW. I will be going through the overall vehicle design, how I built the Arduino circuit, the code, and the PID circuit code, and then how I did the lab, including the front and the block design for LabVIEW. So, as far as my vehicle design goes, there is a master Arduino which controls the left ultrasonic sensor, front ultrasonic sensor, and right ultrasonic sensor. These sensors are there to detect obstacles and maintain position on the road via steering and communication with the LabVIEW. The LDR allows the headlights to turn on automatically when it becomes dark, and the bumper switch to detect a crash and shutting the entire thing down. There's also a motor which moves the car forwards and backwards via the RWD and the L293D chip. The batteries are there to power the entire car. The car is also made up of three Arduinos, with one being the master and two the slaves. The first slave controls the magnometer, which helps with the direction of travel, and the second slave Arduino controls the input from the camera network. Camera network is represented as A, B, or C in correspondence to the type of bend that the car is approaching. For my Arduino circuit, or my Tinkercad circuit, it's been arranged so that the Arduino is easily visible, with it having three Arduinos and four breadboards, three being small breadboards and one being a breadboard mini. The master Arduino is connected to the top left and top right breadboard, with the top left breadboard being connected to the three ultrasonic sensors, left, front and right. It also houses the LDR and the two LEDs. The top right breadboard is connected to the L293D bus, the crash button, the servo, which is used to steer the vehicle, the motor, which is used to move the vehicle up and down, and the two 9-volt batteries, which are used to power the entire car. My first slave Arduino, located on the bottom right of the master, contains a magnometer and is connected to a smaller breadboard. The second slave on the bottom left of the master is connected to the left breadboard, which houses the camera and three push buttons. Each button responds to a type of bend, which is picked up by the camera to let the vehicle know which way to turn, either soft, medium, or hard. This is then inputted into our LabVIEW. The code in my first Arduino, the setup function is executed once the program is first run. It sets the mode of digital pins by the program and initializes the serial communication. The loop function is executed repeatedly, allowing the program to read the sensor data, control the LED lights and motors, and send data over the serial connection. The program uses an ultrasonic sensor to measure the distance to an object in front of the motor. It does this by sending a pulse of high voltage from the trigger pin, which once the pulse hits an object is reflected back to the sensor and detected by the echo pin. The time it takes for the pulse to travel to and from the object is used to calculate the distance. It reads the ultrasonic sensor using the pulse in function. The program also reads the data from the LDR, which is used to detect the amount of light present in the environment. The program uses this data to determine whether the LED light should be turned on or off. If the light is below a certain threshold, the program turns the LED light on, otherwise it remains off. The program also uses a servo steering motor, which is attached to the steering wheel, which can be rotated at different angles to control the direction of the motor driver. The program uses the servo class to control the servo motor and rotate the steering wheel to the desired angle. Finally, the program receives the data over the serial connection and uses it to control the speed of the motors. The program uses the map function to map the received data and range of values, and this can be used to control the speed of the motors. The map data is then used to set the speed of the motor using the digital pins connected to the motor driver. The second slave device controls a magnometer, and as you can see in the code, a magnometer is a device that measures the strength of a magnetic field in a given location. In this case, the magnometer is stimulated by generating a magnetic field based on the current heading of the device. This is determined by the potentiometer. The stimulated magnetic field is then sent over the I2C communication bus, allowing it to be read by other devices. The program uses the WireH library to communicate over the I2C bus. It uses the wire begin function to initialize the I2C bus and the wire on request function to register a callback function that will be executed when a request is received over the bus. In this case, the callback function transmit values, which is used to transmit stimulated magnetic field data. The program also uses the analog read function to read the current value of the potentiometer, which is used to determine the current heading of the device. The heading is calculated by mapping the potentiometer value from a range of 0 to 360 degrees using the map function. The magnetic field is then calculated using the cos and sine functions, which generate our x and y components of the magnetic field based on the current heading. The magnetic field is then stimulated by adding random noise to the calculated values using the random function. Finally, the simulated magnetic field data is sent over the I2C bus using the wire.write function. Finally, for our second slave Arduino and third Arduino, this reads the input of the three sensors and outputs a character serial port based on the state of the sensors. The sensors are connected to the digital pins 5, 6, and 7, which are referred to as hard band, medium band, and gentle band respectively. The setup function initializes the serial port and the I2C communication using the wire library and digital inputs of the sensor. The loop function continuously reads the state of the sensors and outputs a character to the serial port based on the state of the sensors. If the sensor connected to pin 5, hard band is activated and the character C is output from the serial port. And same if it was connected to pin 6, the medium would be activated, and if it's connected to pin 7, it would be the gentle band, and you would get the character A in the output serial port. The transmit bands function is not called in the loop function, so it will not be executed. This function reads the state of the sensors and sends a character over the I2C communication based on the state of the sensors. If the sensor is connected to pin 5, it's activated character C, and then 6 it would be character B, and then 7 it would be character A, respective to their hard band, medium band, and gentle band. I will now quickly display the LDR functioning. As you see, this is raised. The LEDs are no longer on, and if we go to the potentiometer and look in the Arduino, we can see that as I change the potentiometer, a different angle is given, as well as if we change the sensors, there is also a different output with respect to what the sensor can face. We can also see that by selecting different buttons on the camera, a different output is given. Moving on to the PID code, we can see that it is intended to control the speed of the motor, because this program uses an encoder to measure the speed of motor and potentiometer to spec the desired speed. The program then calculates the error between the speed and the desired speed and uses the PID controller to adjust the output of the motor in order to minimize the error and maintain the desired speed. The program begins by defining several constants. Throughout the program, motor controller 1A and motor controller 1B constants used to store the pin numbers and the control of the motor pins, and encoder pin 3 and encoder pin 4 constants are used to store the serial pin numbers of the encoder pins. The pop pin and scaling constants are used to store the pin number of the potentiometer and the scaling factor for the encoder measurements, respectively. The program also defines several variables that are used to store the current desired speeds of the motor, as well as the various errors in the parameter used by the PID controller in the setup function. The setup function is used to initialize the pins, set up interrupts to count the pulse from the encoder, and set the initial value to the speed used by the PID controller. The main body of the program is contained within the loop function, which is executed repeatedly. The loop function begins by reading the current value of the potentiometer and using the map function to convert a range from -255 to 255. The value of this is used to set the desired speed of the motor. The function then calculates for the speed of the actual motor using the encoder measurements and the scaling factor. The function then calculates the errors between the actual speed and the desired speed using a series of equations. The errors are then used by the PID controller to calculate the output value for the motor. Finally, the function prints of the various errors and speeds on the serial motor for diagnostic purposes. Moving on once more to my MATLAB. Unfortunately, my MATLAB was not as successful as my Arduino, as not all of it is functioning. Here is my front and block view. We'll first demonstrate the fuzzy input, and this is the fuzzy system designer I used, and here are the rules for my fuzzy design. The Arduino output from my serial monitor is an input into the lab view. This then goes into my string byte array, which returns a number of elements, and for me this is 6. These 6 elements are converted into output via the ASCII table. This then goes to the right sensor, left sensor, front sensor, the lights, bumper, and brakes also. These are then displayed accurately after being converted on the front panel. As you can see here, when I input the data from my Arduino into the lab view, the sensors, the dials change and the front panel displays what is necessary. Thank you.